Okay, we will continue the study of these polynomials. In the previous video we constructed a second degree polynomial which supposedly followed the curves of our original function f much closer. But clearly if you look at a point which is sufficiently far away from our base point a, then again the second degree polynomial will not fit the function very well, and again we continue the procedure to look at a higher order derivative, first at the third order derivatives, and we construct a third degree polynomial and so on. So now I will give the general construction, and to do so I need some notation, and this notation is the following. It is the notation n factorial, which means the product of n minus 1 times n minus 2 up to 1. And in order to be consistent we have to define 0 factorial to be equal to 1. Now we get to the definition of the Taylor polynomial. And you can find this on page 272 of the book. And to do so, we let I again be this interval around base point A, and we suppose that f is a function defined on this interval I, and that this function f is n times differentiable on the interval I. So we have the situation of the interval I containing our base point A, and we have this function f, and we look in the neighborhood of the point A. Now what is the nth order Taylor polynomial? And the nth order Taylor polynomial of f is based on a certain point A that you can specify, and this is the polynomial p indexed by n to indicate the nth order and A as the base point. It's equal to the function value at the point A plus the first derivative multiplied by x minus A plus the second order derivative evaluated at the point A multiplied by the difference between x and A squared divided by 2, which is equal to 2 factorial, 2 times 1, plus the third derivative evaluated at the point A multiplied by the difference between x and A to the power 3 divided by 3 factorial, which is 3 times 2 is 6, and so on. And the last term is the nth derivative evaluated at the point A multiplied by the difference between x and A to the power n divided by n factorial. And these numbers, these 2 factorial and 3 factorial and n factorial and so on, are chosen in such a way that the following property holds: that to guarantee a certain closeness to our original function, that if we evaluate our polynomial at the point A, we get the same as the function evaluated at the point A. If we look at the first derivative at the point A of this polynomial and the first derivative of the function, then they are equal. The second derivatives are equal, and so on, up to the nth derivative of function and polynomial. Now, what I showed you in the first video is that if we differentiate the polynomial of degree n plus 1 times, then we get 0. So the n plus 1th derivatives at any point and higher order derivatives are all 0. Let me give some examples, one on this in this video, and then in the next video a few more. So we continue the example of our function f being equal to sine of x and our base point A. being equal to 0, and we look at the fourth order Taylor polynomial. Now, what do we get? We know that the derivative of sine of x is cosine. The second order derivative is minus sine. The third order is minus cosine. And the fourth order is again equal to, we are back to sine of x. And minus cosine of x. So what do we get if we compute the fourth degree polynomial at base point a equals 0? It is function value at point 0 plus the first derivative cosine of 0 evaluated at base point 0 multiplied by the difference between x and our base point 0 plus the second derivative is minus sine evaluated the point at the base point 0 multiplied by the difference of x and 0 squared divided by 2 plus the third derivative of our function evaluated at point 0 is minus cosine of 0 multiplied by the difference of x and 0 to the power 3 divided by 3 factorial plus the fourth order derivative evaluated at our base point a equals 0 multiplied by the difference between x and a to the power 4 divided by 4 factorial. And what you see is that most of the terms disappear. Sine of 0 is always equal to 0. Cosine of 0 is equal to 1. So we get 1 times x. This term cancels. Here we get minus cosine 0 is minus 1 divided multiplied by x to the power 3 divided by 3 factorial is 6. And the last term cancels because sine of x is equal to 0. And if we now compute this fourth order polynomial at the point 1, then we get approximately the value where it is. I computed it somewhere, 0.833 and so on, and recalling that the value of sine of 1 was equal to 0.84 and something, then you see that this is already, say, close enough. I mean, it's just the first decimal is already okay, and there's only difference in the second decimal. So we start to approach our function value sine of 1 already much better with this fourth degree polynomial compared to the first degree polynomial that we computed earlier.